Morning, everyone. Can you guys hear me okay?
Good morning, sir.
Yes,
Good morning.
Good morning.
Good morning. Okay, so let me start recording. Just waiting for the recording to start. Okay, so any questions from our previous lecture? Did everyone understood what fork does? Because if you have difficulty understanding what fork does, you might have a problem understanding the remaining part of the lecture, right? So it is important that you understand what the fork does, right? So let me just briefly reiterate. So as I said, fork is the only system call or function, right? The library function that we have, which is returned twice, right? Which returns two different values. After duplicating the memory for data area and the code area and the context for the parent and the child process, right? So initially you have the original process in the memory. The memory map is then copied when the fork system call is issued by the operating system. So you get a copy of the parent process and you get a copy of a child process. As I said, the context may have different values for the process ID, parent process ID, and so on. However, the data area and the code area is exact replica, right, of parent and child. And then for the parent process, the PID value which is returned by the fork is going to be the child process's PID, whereas in the child process, it is going to return a value of 0. And that is what we use as a condition here to check whether if the PID is greater than equal to 0 or not equal to 0, that means it is a parent process, and we put the statements here which are going to be only executed by the parent process. And if the condition is false, then we in the else part we run the we run these commands which will be basically or these statements which will be executed only for a child process, right? So this is how we identify what is a parent and what is a child process. And then if there are any statements which are beyond the if statements, there is no condition there, then those statements will be executed by all the processes, right? All the previous processes that were created. So in this particular case, there are only two, parent and child. So both the parent and child process will will execute this particular line. Okay. So this is what the fork does. Now, I briefly mentioned that you have a copy of a data area when you when you do the fork, right? When you issue the fork command. So which means that any changes that you make. So when you look at this particular picture over here, right? So we have the data area for a parent and data area for a child. So that means that if the variable, you will have the same variable names here as well as here, because originally when you did fork, it is exact replica over here. But once the code in this particular area, right, in your if statement, if it changes any value of the variable, right, then that value is not going to be available in the child process, the updated value, right, because the updated value is only applicable to the parent process. Similarly, if you update that variable here, then that value is only available for the child process. So the scope of the variable is local to the process, right? It is not global for all the processes, is what I'm trying to say. Because even though the variable names are same, it has two different memory addresses, right? So there is a memory address for the parent process and there is a memory address for the child process. Okay, so we are going to take a look at an example of that one now to understand how the scope of the variable changes. When you let me just be with this slide only here. So if you look at this particular code, what we have is we have a variable called I, and that is initialized to 1, right? Now this initialization is done before the fork is done, right? And we are printing the value of that I before the fork. Now at this point we only have one process, which is your original process, right? Then we do the fork. So when we do the fork, obviously the copy of this I will be made also in the child process. So there will be a parent process where the I variable exists, and now it is going to be duplicated for a child process, right? So now you have two variable i's with two different addresses. So the name of the variable is the same, right? However, there is a variable I in a parent process and there is a variable I in a child process. Okay. So at this point, in your if statement, if you make any changes, so for example, we are making changes to the I variable, we are just adding 5 here, right? So we are printing the value of I before the update and we are printing the value of I after the update. So we are expecting that in the parent process, the value of I will be here, it will be 1, and then here it will be 6 because 1 plus 5. Now, if we come down over here in the child process, again, as I said, the value of I at this point, right, when we are printing this one, again, it is going to be just 1, right, because the original value of I was duplicated for the child process, right? The original value of I was duplicated in the child process's data area. So therefore, you have the value of I as 1 here as well. Now we are adding the 10, right? We are adding 10 to I, which will give me 11. So at this point in the parent process, the value of I is 6. However, here the value of I is going to be 11. So you can see that even though it is the same name variable, but two memory references or two memory addresses for the same variable, one for the parent process, one for the child, and therefore really they are two different variables, right? They are really two different variables for which are local to that particular process. Okay, now we have one more variable which is actually declared here. So you see, I have actually done the declaration of the variable inside my parent process. Okay, the declaration of the variable is not outside before the fork. What it means is that this variable is only declared and available in the parent process's data area. This variable is not available in the child process's data area at all, right? Because the declaration of this variable is not before the fork. So therefore, this variable is not duplicated in the child process's data area. Okay, so you can also declare a variable local to a particular process, a parent or a child, and that will only remain as a local variable. Okay, so this is something also you can do, and there is an example that I am showing you. So what I will do is first I will comment this line out because I am trying to access the parent's local variable over here, which will actually throw an error to me, or maybe we can just do that. So let me just run this code, or actually first compile this code. Okay, So GCC fork where scope.c minus o fork where out. Okay, so you see that I get an error when I do the compilation. And where am I getting an error? I'm getting an error at line number 28. Okay, and line number 28 is basically this one, right? And if you go to the code, you will see that also line number 28 is this one, which is this one. So I'm getting an error saying that iParent, right, in this child process is not a valid variable. That is the error I am getting here, and which is correct, right? Because iParent is a variable declared in the parent process, and it is not actually accessible or available in the child process. Okay, so that is why I'm getting this error. So you can see that because it's a different process, these variables are local to that process, right? Once it is declared inside your if or else part. Now if I comment that line out, which is trying to print the value of iParent, and then I try to compile it, I should be able to compile without any problem, right? Because now I'm not accessing this iParent variable in my child process. And now if I try to run this program, this is what I will get, right? So basically, this is the I value before the fork, right? This is the I value before the update in the parent process, I value after the update in the parent process, and this is the value of iParent variable from the parent process, right? Now, this printf is the last printf after the if else part. So you can see that there are two printfs over here, right? Which is actually printing both parent and child execute I equal to, right? So there also it is going to print a value of I, but for each process individually, right? So parent will also execute this line and child will also execute this line. And then it will say that which PID is terminated. Okay. So we can see that for the parent process, when that line is executed, again, the value of I is 6. And then now the parent process is terminated. Now the child process is running, although child process will be running concurrently, because the child process takes time for core allocation. Most of the time what will happen is child process will be lagging behind the parent process, right? That is generally what we observe, but it is not always necessary also. Okay, so here now you have the child process starting, and you can see the value of I before the update in the child process. Again, it is 1, right? So you can see that here also before update it is 1, here also before update it is 1, because this is the exact replica, right? This is the exact replica of I just after the fork. Okay, and then in the child process we change the value of I, which is the new value which is printed over here, and then these two lines after the if else part, which is printed over here. So what I'm trying to say is that the variable I has a local scope for individual processes once you do the fork, and if you declare a variable within the scope of the process only, these variables are only available for that process and not available for any other process. Okay, that is what the example is trying to show you. Any questions? Okay.
Sir, can you
Yeah.
please open the code? A small doubt I was having.
Yeah.
In this, most of the C codes, they generally execute line, means they go line by line in the downward manner. So after executing the if block, how is the function like after reaching the end of the main function? Is it going back to the else part or?
No, no. So that is what I'm trying to say. See, this part of the code, see, once you do the fork, right? Once you do the fork, you actually have two process IDs. You have two process IDs. So the way that code executes, it is not executing sequentially. Let me go back again here. Okay. So what will happen is this process is a different process. This process is allocated to, let's say, core 1. And this process is allocated to, let's say, core 2. So core 1 also has a program counter, core 2 also has a program counter. So basically what I'm trying to say is that both processes are actually executing parallelly, simultaneously, concurrently.
Okay, so because of the if else, firstly the parent process executes, then the child process.
No, not even that. Not even that. See, most of the time, what happens is that once the fork executes, see the parent process was already allocated a core, right? So it was already running, right? Because
Yes.
that was the original process,
Yes.
right? So that's why it actually didn't take more time to run the parent process here. Okay, for the child, what happened was once the process was created, the PCB was allocated, right? The process control block was allocated, the data area and memory and code area was created, and then the core was allocated, the CPU was allocated for the child process. So because of that additional time that it requires to start the child process execution, that's why you are seeing these lines as here. But it is not always necessary that these lines will come here. If I run like 100 times, it may be possible that sometimes you will find that the child process code runs even sometimes earlier. Okay, so you see, in this case, I think, well, maybe not. I mean, if you try to run it like 100 times, you might find sometimes that your child process also has started, around the same time as the parent process. So in this case, I'm not able to replicate that scenario for you. However, it is a fact that it is not. See, basically, what we have done is this: the once the fork is done, the program counter for the core where the parent process is supposed to run will start executing from here, and the program counter for the core where the child process is allocated will start running from here, because it will find out that this condition is true for child process and this condition is true for the parent process. So in reality, both of this code, this part of the code and this part of the code, is running simultaneously on two different processors.
Okay. Okay. Yes, sir.
Understood?
Yes, sir.
Okay. See, this is the problem. Sometimes, you are not able to replicate the scenario, by execution, but you have to visualize that, right? I mean, you have to visualize that. Sometimes it does work. I mean, I've seen it working, but I guess today it's not. See, it depends on the operating system. So, it's not always easy for replicating such scenarios, but keep that in mind that once the fork is done, there are two processes. Both the processes may be allocated to two different cores or CPUs, and therefore both of them will be running simultaneously. Okay, so it is possible that you get this printf, and then immediately after that you may get this printf also. It is possible. Okay, all right, hope it is clear to you.
Yes, sir.
Okay, so now we want to take a little bit more complex scenario here, and you can see that I have this code over here, right? And all this code is doing is it is doing forks, multiple times. So the question that I would ask you is that how many total number of processes will be created when these lines are executed? Okay, and which processes will be executing which line, right? Whether the first fork, second fork, third fork, whatever it is. So the way we will be able to figure that out is we have to draw a tree. Okay, and so I'll start doing that on this page, right? So let's assume that your original process, which is this one. Assume that we have original process. Let me call this as original PID, and let's assume that that is a PID number 10. Okay, now once this main function started, the first fork is getting executed. Okay, so the first fork gets executed by this particular process, which means that that process is going to be forked into two more processes. Okay, although one becomes your parent process, right? So I'm going to call that as PP, parent process, and that will have a PID of 10 again. But because remember, your original process basically becomes a parent process, right? And then you get a new process, which I will call it as CP, child process, right? And this will have a PID of 11, let's say. Because usually the PID, if you would have noticed when we execute fork, usually the PID of the parent process is incremented by 1, and that is the child process's PID. Usually that is what we see. Okay. Now, so that is about this particular fork. Okay. But now there is another fork right next to it. Now, which processes will execute this fork? That is the question, right? Whether this one, or both. Now, the point is, we don't have any if statements over here, right? We are not checking the PID which is returned from these four, and we're not checking that PID, and we don't have any if statement over here. So what we have learned is that anytime when you don't have if else part after the fork, any statements that you put after the fork will be executed by all the processes that are created, which means that this fork will be executed by the parent as well as the child. Okay, so which means that this fork will be executed by this one as well as will be executed by this one. So which means I get two more processes here, right? And let me call this as PP1, and this will be again a PID of 10, because again this is the original process. In this case, if you just look at this subtree, right? If you just look at this part of a subtree, this is my original process, and that original process becomes a parent process now. Okay, and then I get CP1, and this will have a PID of, now here I cannot use 11 because I already have 11 ID for one of the child processes. So therefore, this will be a PID of 12. Okay, which is the next PID available. And then the same fork will also be executed by this child process, and therefore I get again two more processes here, right? So I'm going to call this as CP, let me just call this as CP2, right? And this will be PID of 11, or actually let me just keep that as CP because that is my first child process. So let me, well, here I've used one. It doesn't matter. I mean, you get the idea. So the PID equal to 11 here, which is basically the same process. So this if you look at just this subtree, right, this is my original process, and therefore this will become the parent process. And then I get another child process, right? I get, let's say, CP3, and sorry, this will have a PID of 13, right? So I get PID 10, 11, 12, and 13. So I get 4 processes out of this one when I execute this second fork. Now again, if you look at the third fork, as we can see, we don't have any condition, which means that this fork also has to be executed by all of these processes, right? So after the third fork execution by all these processes, what do I get? Again, I get 2 from here, 2 from here, 2 from here, and 2 from here. So here, again, this is my original process. So this is PID 10. Then I get PID equal to 14 because 13 is already used, 12 is used, 11 is used. This is my original process in this subtree. So here I will have PID of 12 and then PID of 15. Here I will have PID of 11 and PID of 16. Here I will have PID of 13 and PID of 70. Right? So you see that 1, 2, 3, 4, 5, 6, 7, 8. 8 processes have been created when I do these 3 fork execution in sequential order without any if condition. What does it mean? It means that the number of forks without any condition, if you execute, then you basically get a binary tree. Right? You basically get a binary tree, and binary tree, the depth of the or the number of leaf nodes that you get in a binary is 2 raised to n, where n is equal to number of forks. Okay, so this is what the value you get, or the number of processes you get if you don't have any condition. However, if you have a condition here, for example, okay, so let's assume that I store the PID value for the second fork, and then I check a condition here. If PID greater than 0, then only execute this fork. What happens here now? So obviously for the second fork, when I executed, I get these 4 processes. Which is fine. However, out of these 4 processes, only 2 processes, which are the parent processes, are allowed to execute this fork because of this condition, right? Which means that this is my parent process and this is my child. This is my parent and this is my child for this subtree I'm talking about, right? For this subtree I'm talking about. So which means only this parent process is going to get the child PID value as greater than 0. However, for this child process, the PID return value will be 0. PID return value will be 0, right? So therefore, this child is not going to execute the third fork. Similarly, this child is not going to execute the third fork. So if I have this condition before the third fork, then only this process will execute the third fork, and this process will execute the third fork, which means I will not have these processes. Well, I will have this one process, right? Not 2 here. Okay, so which means that my number of processes is 1, 2, 3, 4, 5, and 6. So I get 6 processes if I have this condition over here. Okay, so again, you can basically play around with these conditions and determine how many processes you need and what you need each process is for, and you can basically use these kind of conditional constructs with the fork condition also to do that. And you can also use your relational operators, right? So I can also use relational operators as and or, right? And depending on what this and does, and depending on what this or does, it will execute a different set of fork. Different set of processes will execute different set of forks, is what I'm trying to say. Okay, so this is again an important aspect to understand how the fork works. Okay, now if you recall, we said that generally in all the operating systems, primarily Unix based operating system or Windows operating system, it is allowed to have both the processes run simultaneously, child and the parent. And also, if the parent process has less amount of work, or it is a process that finishes earlier than the child processes, then operating system does allow that, meaning that parent process is allowed to terminate before the child process. Okay, so it is allowed, it is valid scenario. But then we said that if the parent process does not read, right, if the parent process does not read the exit status, then the child process will become zombified. Okay, but now if the operating system says that parent process can terminate earlier than the child process, then what will happen? Right? What happens to the what happens to the child process? Will it become zombified every time? The answer is no. Because what happens is that whenever the parent process terminates first, the child process will be adopted, right? Will be adopted by the mother of all process, which is an init process. Okay, mother of all process, which is an init process. So that means there is always a parent process for any process in the system. There is always. If there are no parent, no regular parent that is there, then init is the parent. So init is always going to be there, acting as a parent process for any child process, okay, whose parent dies first or terminates first. Okay, so again, let us look at an example of that, which basically we call an example as an orphan child, right? So what we have done is, in this example, we have the parent process, right? And the parent process is only sleeping for 5 seconds, right? So we are going to put a 5-second sleep time for parent process to sleep. And for the child process, we are putting a sleep time of 15 seconds. And before putting the child, so you know why we are doing that? So that the child process will always terminate after the parent process, right? That is what the scenario we want to illustrate over here. And what we are doing is we are going to read the parent process ID for that child before the sleep mode, as well as we are going to do the same thing for after the sleep mode. So what are we expecting? We are expecting that at this point, right, at this point, the child process is having the parent, which is this parent process, this particular parent process, right? However, after this 15-second sleep, because this parent process has already terminated, the parent process for this child process must be changed to the init process. So when you look at this PPID for the child process, we are expecting that PPID to be of init process and not for this particular parent process. That is what the scenario we are trying to illustrate here. Okay, so let me run that code and so right now the parent is waiting, and now parent is finished. Okay, so you can see 3252 is the parent's ID, which is finished. Okay, but now child is still running, and now the child finished here after 15 seconds. Okay, and if you look at the child processes, print statements. So this is the child process print statement, right, before the sleep time. Okay, before the sleep time. So you can see that the parent process was running and the child process was also running simultaneously. So again, the person who was asking me question about whether the child and parent run simultaneously or sequentially, you can see in this example that this printf is coming before the parent process dies. Okay, why? Because the child process is also running simultaneously along with the parent process, but on a different processor, different core, different CPU. Okay, so you can see that here you have the child process ID as 3253, and the parent for that child process is 3252, which is our own parent process. Okay, which is our own parent process. So originally when the child was created, the parent process is 3252, which is our own parent. However, once the parent dies, once the parent terminated, then after the 15 seconds of sleep, when you get this information, you will see that the parent process ID for the child is now a 1847, not 3252. What is 1847? Let us look at PSAJXF. So 1847 is this process. What is this process? It is a system MD process. And if you recall, when we were talking about the init process, which is the mother of all process, I had told you that system MD is a newer version of the init process, which is now used in most of the GUI based Unix based operating systems. Okay, so but if you see the parent of that, right, which is the ID number 1, process ID number 1, and that process ID number 1 is nothing but the original init, right? I'll find it somewhere here. This one. So this is the original init process, which was used for operating system, the older versions of the operating system, and the newer versions of the operating system. They've created a new envelope, new wrapper on top of the init process, and that basically is called the system MD. Okay, so system MD is also another name for init process, but it has some more functionality for GUI based system. So that's the reason 1847 has become the parent of that orphan child process. Okay, so basically again, init is the process who is taking over or who is adopting the child once that once that child's real parent actually terminated earlier. So this is an example for showing you that there is no process which will never have a parent process. There will always be a parent process which will be your init process. Questions?
Sir, what will be the parent process? Which will be the parent of init process?
So as I said, the parent of the original init, which is the number 1 process ID, right? It doesn't have a parent. So you can see that it is showing the parent process ID as 0. Okay, but if you look into this list over here, you will basically find this as the parent process ID, and this is the operating system. This is the starting point of the operating system. So there is no PID with 0 value. You will find here the original operating system is the is basically the process 0. So here in the list you will never find PID equal to 0. See, there has to be always a root node, right? Some root node has to be there. So that 0 is a root node which only operating system knows about. And then it creates an init process, which is basically, as far as we are concerned, right? System developers are concerned, that process is the root of all the processes. Okay, which is this one. Okay. All right.
But sir, you said that once parent process is terminated, the child process will be adopted by init process. But sir,
Right.
here child process is adopted by system D. So
that is what I am saying. System D is the advanced version of the init process. Init process was the original init process, which was on the non-GUI based Unix operating system. The new GUI based operating systems have additional functionality in the init process, and that new application which was created as an init process is called system MD. You can Google it up if you don't believe me. Right, so system MD is basically new version of init process is what I'm trying to say. That's all. So what they've done is it is
Okay.
system MD is a wrapper around the old init process. So old init process is still there, it is still running. On top of that, a new init process has been implemented, and that new init process is called system MD. Okay.
yes, sir.
Okay. And like I said, if you don't believe me, you can Google it up. So now the point is that we said that the child process can become the orphan process in case if the parent process terminates, meaning that it becomes orphan temporarily and then it is adopted by the init process, right? However, if you want to ensure that the parent process does not terminate before the child process terminates, then we can use a wait system call, right? So wait system call, if you recall, I told you that there is a wait system call which will make sure that the child process will terminate, then only the parent process will terminate, right? So you have two versions of the wait system call. One which does not have the process ID provided over here, which means that if there is a parent process who has created multiple child processes, whichever the child process first terminates, the wait system call will come out. Okay, so which means that if you have 5 child processes, you have to wait 5 different times. So you have to issue 5 different wait calls, okay, for each of the child processes. However, if the parent, for the parent, you only want to make sure that it waits for a particular child process, okay, then you can provide the child processes process ID as a parameter in the second second version of the wait. Okay, so in our example, we are just going to show you the first version. I mean, second version will basically work in the same way. There's no difference at all, really. So here, as you can see, we have a sleep for the child process, right, for 10 seconds. And we don't have any sleep in the parent process. However, we have this wait over here. So this wait system call, which you issue in the parent process, will ensure that the parent process does not fall off the last statement. It will basically be locking, right? It will be locked over here. The parent process will be locked or waiting over here for the child process to terminate. And only once the child process terminates, the wait system call will come out, right? Will be finished, and then the return value that you get from there is the PID of the child for which the wait process has returned, right? So that is the information that you get. There's an additional information that you get in the status field, which I'll talk about it in the next 2-3 slides, right? So let's wait for that one, because there are a lot more stuff that I need to explain over here. So for now, you just have to understand that you have to pass an address of an integer, where the operating system also returns some data. However, the wait system call is a blocking call, and that call will be returned back only when one of the child process is terminated. Now, in this case, since there is only one child process, it will be returned back. It will be coming out, or it will be coming back to the parent process execution once that child is terminated. Okay, so that is what the example is showing you.
Sir?
Yeah.
Sir, if the child process gets locked in a deadlock, then is there a maximum upper limit till what wait will wait?
No, there is no upper limit, and it's a good question. So the point is that then you also made your parent process deadlock. So the only way you can kill those is by using that kill command which I showed you yesterday.
Okay.
Or did I show you that yesterday? No, I didn't show you that yesterday. I'll be showing you that today. So there is a kill command which can forcefully kill the processes. Okay, so I'll show you that how to do that. But yes, there is no way to actually there's no way. If the process is in deadlock mode, then the only way is you have to forcefully kill it. So now you can see that the parent process is waiting for the child to terminate for that 10 seconds. And once the 10 seconds are elapsed, then the child will finish first, and then the parent will finish. So you can see now that after 10 seconds, this child process is terminated, and then now the parent is terminated. Because and this message, if you see, this message is actually coming from the parent process's code. Okay, so this child PID is what is returned back to us, and that is what is being printed here, right? So this PID is, we know that in the parent process it is the PID of the child process, and that is what is printing here. But I could actually do this also. Let me just change this to child PID. Okay, and that child PID will also give me the same PID number. Let me recompile GCC failed. Okay, and so same thing, right? So you get 3368, which is your child, and that is what the child process terminated. Okay, so you can either use you can either use this particular variable as the child process is PID in the parent process, or you can use the one which is returned. Why we have to ideally use this one is because if you have multiple child processes, each time you will get a different process ID over here for the child which now actually got terminated, right? So it is better to use this child PID because that is the child which has terminated now, right? Unless you had a single child, in that case, this PID and this child PID will be same. Okay. All right. Now, we mentioned also that your child process, if it has exited, if it has terminated, but then the parent process has never read the exit status, then your child process will become zombie. Okay, so this is the scenario we are going to replicate here, that the child process has terminated, however the parent process is not, or is too busy reading the is too busy and it's not reading the exit status. Okay, so how do we replicate that? How do we cover that scenario? Is basically what we have done is we have put the parent process in a huge sleep, right? So the child process is exited with this particular exit code. I've just given some number here. It doesn't have to be 42. It can be anything, right? But then the the parent process is not reading the exit status, okay, because it is sleeping for 1,000 seconds, which is almost unlimited amount of time, right? I mean, I guess few hours or days. So when this happens, the parent process is not reading the status, and so the child process will go in a zombie state. Okay, so that is what the scenario will happen, and what we will do is we will run that zombie example. Okay, so the child process is 3375, the parent is 3374. And if I want to see what is the zombie state, what I need to do is I need to actually go to the new terminal window and I need to do PSAJXF. So you see that 3374 is the process ID here, which is my parent process, right? So this is my parent process, okay, and this is my child process. Okay, so if you look at the status column, this is the status column in my PS command, and that status column is showing you here as Z. So that Z indicates that it is the zombified state. Okay, similarly, if you look at this defunct, so that defunct keyword also indicates that my child process is zombified. Okay, now because I have executed my parent process in the terminal window, one way to terminate this process is by pressing Ctrl C. Right, so when I press Ctrl C, my parent process will be killed. Right, my parent process will be killed, and therefore the child process will become orphan. Right, so my parent process is killed, so therefore the child process becomes orphan. But then the child process will be inherited by init process, and the init process will read the exit status of the child process, and therefore the child process will also terminate. Okay, so now if I run that PS minus AJXF, you will see that I don't have either one of the processes running. Okay, now it is possible that you may be running your parent process not in the terminal window, in the foreground mode. So there are two ways you can run any process. If you want your process to continuously running, right, in the background, and you don't want to keep any terminal window occupied with it, right, or you don't want any person to actually accidentally close the terminal window and turn off your process, right, or terminate your process. Another way to run the processes is using a background mode. So how do you run a process in a background mode? You provide and sign at the end of the executable name. Okay, so if you provide and sign at the executable name, what it means is that you want this process to run in a background mode. Okay, so it will be kind of like a running it inside the memory in the operating system. However, this terminal window will come back to the prompt, right? So you will definitely come back to the prompt and you can run any other commands after that. So the terminal window is not allocated to that particular application or that parent process. Okay. So now if you see, I can actually come back to the terminal window and I can run any other commands that I want. Okay, once my process is started. However, because this process is a long process, sleeping for 1000 seconds, the process will continue to run internally or will be sleeping for 1000 seconds internally. How do I know that? Again, I can do ps minus ajxf, and you can see that that process is still running, right? But it would be running in a background mode. It will be running in a background mode. So again, the parent process is running, and my child process is again zombified, right? Because the parent process is in a sleep mode and it has not read the exit status for the child process. But now the problem is, how do I kill my parent process, right? How do I kill my parent process? Because my parent process is no longer actually running in a terminal window, right? I ran it as a background process. So when you run a process as a background process, and if it is hung like this, then the only way you can you can get rid of that process is by killing it, right? So you have to kill the process to remove that or terminate it forcefully. Okay, so there is a kill command, and kill command I'll actually cover more in detail when we talk about signals. However, just for your this exercise, we are going to use a kill command, and kill command takes one argument, which is the process ID of the process which you want to kill. Okay, so what I will do is I want to actually kill my parent process, which is this one, and so I will get the process ID of the parent process from here, which is 3398. Okay, so I'm going to say kill 3398, which is going to kill my parent process. Again, once the parent process is killed, the child process will become orphan, will be inherited by the init process, and the child process will be terminated also. So once I kill, and again when I do ps ajxf, you will notice that again those processes are gone from the memory. Okay, because I killed, so you can see that that message comes here, right? That this original process is now terminated. Okay, so ps command will also display the message that you killed this particular process in my previous command, in your previous command, right? So this is another way you can you can get rid of the parent process if it is hung or if it is not running the way you want.
Sir, sir,
yes.
sir, what if you do kill one?
Kill one will kill your system.
Sir, so what will happen if you do that?
You can try. It will kill your system. Basically, it means that your system is crashed. You have to shut down everything and you have to restart your system again. After you do kill one, so first of all,
does it allow us, or there is any safety mechanism?
So
as in Windows, we can't delete the
yes,
system.
so some of these processes are only accessed by the root ID. But see, if you are an administrator on the system, you have access to those things, right? If you have a root ID, if your ID has a root access, then you have access to complete system. So point is that the safety check may be there as far as the access is concerned, right? So it is possible that the operating system says that you cannot have access to this process unless your user ID is X and you enter your user ID and password properly. But if you have it, if you have that user ID in the password, you can do anything with it, right? I mean, you have installed VirtualBox yourself, you have installed Linux yourself. there is a root user on that system, and you know that root user and the password. So you are in full control of that system. Right? So don't share that ID and password with anybody else, bottom line, right? This is the reason when you go and work in the company, you will not get a root access to the server. In fact, we have many servers in our college also, and administrators will not give us a root access unless it is absolutely required, and you have to take a permission from the owner of that server. So there are faculties who actually bought servers for their projects, right? And if you talk to the faculties, and if it is really necessary, they might give you an access as a root. But generally speaking, all the servers that we have in DICT also, we don't get a root access. We get a user access, general user access, so that we are not allowed to do things like that. Okay. All right. Now I'm going to talk about race condition. Right. Have you heard about what is race condition in any of the course earlier? Yes, no? Anyone?
No, sir.
No, sir.
Okay. So what is a race condition? So race condition means that you have a single resource and multiple processes are trying to access that resource, and the resources is see, ideally, basically a resource has to be allocated to one process or the other. For example, let us talk about so I'm giving you an example of something which we will cover in threading area. However, that is the truly a race condition example. So for example, let's say you have a variable, okay, and one process or one thread is trying to read the data from that variable, and other process is trying to write the data into the variable, right, or update the value of the variable. Now, updation of the variable and reading of the variable, or maybe multiple process trying to write or update the value in the variable, right? If you do that, only one process should be allowed to update first. Once the updation happens, then the second process can come and update the variable, right, or read the variable. But if both processes try to access the same variable at the same exact time, then what value will be updated or what value will be read is unknown, right? I mean, there is basically a conflict. There is a conflict between two processes because they are trying to access the same resource, and that is what is called race condition. Okay, so race condition means that you're trying to access the same resource for writing and reading, or writing and writing, and that is why you are creating a problem for yourself. So ideally what should happen is there should be a locking mechanism, which again we will look at it when we look at the threading examples. But there are locking mechanisms which will ensure that a given resource is only accessed by one process at a time. Okay, so this is an example that I want to show you. But in case of process management or processes, variables are not shared as we have seen earlier, right? There is a separate data area for the variables, so variables are not shared. But what are the things which are shared? Files. You can have different files shared among different processes. So if you have opened a file, before fork, then the same file handle is, or file descriptor is available in both the processes. So if you use the same file descriptor, so basically what will happen is, we have seen an example of file IO, right? It works like a loop. You have a file, open file, and then you do the fork. So the same file handle is duplicated in the child process. The same file descriptor is duplicated in the child process. So therefore, even though there are two different processes, the parent process and the child process, but they both have the same file descriptor, and they both are going to be able to reading and writing into the same file descriptor. So basically fork will act like a dupe in that case. Okay, so what I'm trying to say is that you can have a race condition in case of process management whenever you use shared files. And that is an example that I want to show you here. So I've not actually used a regular text file, but what I have used is the standard output device. Okay, I've used a standard output device. So basically what we have done is, this is the function which is implemented. In this function, this is the system call which allows me to set the internal buffer of the operating system to null, which means, if you remember, I told you that in the buffered IO, especially for standard output and standard input, we have an internal buffer to the operating system. And initially the data is read or written into that buffer, and then once the buffer is full, or if it is a line buffer, then once you have a new line character, then the data is actually sent to the application or a particular device. So here what we are doing is, we are basically setting the internal buffer to null value. Okay, so we are saying that we don't want to use a buffer for a standard out device. That is what we are doing here. So every single write will be directly going to the screen, okay, without using the internal buffer. Then we are going through each character at a time, the string which is passed over here, and then we are doing the put C, which is displaying one character on a standard output device at a time, right? So you only display one character at a time. Now this function is being called from two different processes over here. So we have a fork, and then in the parent process, it is also calling the function with this long string that it wants to print. And in the child, again, this is the this is the long function, this is the long string which it wants to print. So ABCD is printed in the child process or the parent process, sorry, because you have the condition here PID equal to 0. So actually this is the child process and this is the parent process, right? So the parent process is printing ABCD and the child process is printing 1, 2, 3, 4. Okay, so now what we are expecting is, since we don't have any buffer, we are expecting that both the processes are trying to access standard out, and both the processes are trying to print one character at a time. I'm sorry, I think there is some noise outside, so let me close the window. 1 second. There's some work going on around my house, so somebody's using some tools. Okay, so so that is what we are doing, right? So if the parent process and the child process both are trying to access standard out and it is trying to print one character at a time, we are expecting that the standard out device will have a race condition, right? That is what we are expecting, and this is basically my file, right? That is what I'm considering. It is my file. So I could write it in the file, or I could just put the data onto the standard output. It's basically the same thing. Okay, so now you will see that my parent process started, I guess, here, right? Because it's printing ABCD up to this point here, and all of these characters are only ABCD characters. However, from this point onwards, you see that numbers are also coming, and the alphabets are also coming, right? So numbers and alphabets are jumbled together, right, all the way up to here. So all of this area is where the race condition happened. So both the processes are trying to write data onto the screen, onto the standard out, right? And that is where the race condition happened. However, at this point, the parent process finished. It is able to display whatever it wants to display, and therefore, from this point forward, you will see that only numbers are displayed, because only child process remains, and it is able to access the STD out without the race condition, because anyway the parent process is terminated. Okay, and every time when I run this, you will notice that there will be a different different output, right? Different race condition will happen, right? So here you will find that see here the race condition started actually a bit earlier, right? And it actually went also a bit later. So you have a more overlapping over here. So why it is? Because we don't know exactly when the child process starts running. You know, how much time did it took for child process to initialize the PCB and everything, and then the core allocation. Okay, so this is basically an example of race condition. Questions? Okay.
So for a previous example, when we were using the printf, so why won't the race condition would happen there? Because it is also giving output to the standard output.
See, so printf also uses internal buffer. So
Okay,
if you again, yeah, if you use this command, right? If you use this command, then again printf also will have a similar scenario. Here we are using putc because we want to print one character at a time. Printf allows you to print the whole string at a time. So if you pass the whole string will be printed in one shot. We don't want that to happen, because we want both the processes to try to access the STD out together.
Okay, sir.
Yeah. Okay. Now, if you recall, you know, I did mention that when we actually issue the wait system call, right, there is a parameter that we pass over here. And this parameter is basically an integer value. It's called status. And because it's an integer, it has 4 bytes. The bits of this variable has different meaning. Okay. It basically gives us some information. What information it gives? So there are primarily 2 information that we get out of it. One is the exit code from the child. So let's say here, you know, this exit is executed in the child process, and it returns the value 10. So the parent process can actually read the value from here, you know, which was sent by the child process to the parent process. So you can actually return some code back to the parent process, and the parent process can read that code. So one of the information that is available in my this variable is this value. Additional information that is available is how the child process was terminated, whether the child process was terminated normally, whether there was any error like divide by 0 error or IO error or something, memory error or something like that, or maybe the child process was killed, right, by using a kill command, right? So these different scenarios could happen, and because of which the child process can terminate. So the parent process has a functionality or is able to figure these things out. And so what they have done is, you have this variable, but then there are specific bit patterns that tells you whether the child process was terminated normally, whether there was any fatal error, or whether the signal was sent, meaning that kill command was sent to the child process to kill that child process, and so on. Now we don't have to remember the bit patterns. What operating system does, they provide us the macros, and the macros will actually specifically check for those specific bits, and it will return us true or false. Okay, so these macros are returning us true or false. So you can see that if you use this macro, it tells us that if the child process has terminated normally or not. If you want to read the exit code, right, exit status code, then you just use wexit status macro. If you want to know that if the child was killed by some signal, then you can use this particular macro, and so on. So some of these macros we will use currently in this example, and some of these macros we will actually take a look at when we learn signals, right? which is a different chapter, right? It comes under inter-process communication. The signal comes under inter-process communication, and that is what we will look at when we look at IPC signals. Okay, but for now we are going to take a look at few of these macros. I think 3 or 4 of these macros. So the first thing that we do is that we use this exit status macro, and this is going to read the exit code. So whatever this value that you are returning from the child process to the parent process is going to be read by the parent process. Okay, and we are going to display that. So you can see that the macro takes this status variable as an input, right, as a parameter. Now, if there was no, if the child was terminated normally or not, we can actually check using this particular macro. So if this macro returns me true, then we are just going to print that the child was terminated normal. If the child was killed or there was a fatal error or something like that, you will be able to find out that if the child was killed, right? If the child was killed using a kill command or something like that, then this macro will turn me true. Now you can also find out that which signal was sent to the child process. So again, this part you may not be able to understand right now because we have not studied signals. And again, the same example I'm going to cover when we cover the signals, right? However, I just want to tell you that if you kill your child process, you will be able to understand that using these 2 macros. Okay. If there was any other abnormal termination, then you go to this third else part, and that is how you come to know about any other type of abnormal termination. So in short, what this example is showing you is that parent can figure out how the child process was terminated and what was the exit code that was returned by the child process to the parent process. Okay. So in order to run this example, first what we will do is we will have the child process terminate normally without any issues, right? So let me just run. And here I'm not going to kill the child process. I'm just going to wait for the delay, right, or sleep time, and that sleep time is 10 seconds. So I'm going to wait for 10 seconds sleep time and let the child process terminate normally. Okay, so 10 seconds are elapsed. Now we can see that these lines are coming from the parent process. Parent process is saying that the child with PID of so and so is exited with exit code 10. Right, so it was able to read this value using this particular macro. Okay, this macro, and that basically is reading this value here. Okay, it's reading this value here. Okay, and then because I let the child process terminate normally, this macro would return true, and therefore this line is also printed, right? That the child process terminated normally. Now we are going to say that we are going to kill the child process in between the execution. So that means it is not going to be a normal termination. Okay, so I have to be quick in killing the child process. So let me just type the kill command here, and then immediately after that I have to provide the process ID of the child process. Okay. So child process is 3561. I'm going to call 3561. Okay, so I've killed the child process, right? I've killed the child process. Now I go back here, and you can see that this information is different than this information, right? So here in the second execution, what we are getting, it is exited with code 0. Why 0? Because the child process never had a time to actually execute this exit 10, right? It was killed while it was in a sleep mode, right? It was killed while it was in a sleep mode. So in the sleep mode, it was killed, and therefore the exit code is 0. So the default exit code will always be 0. So if you don't actually write the exit command, if you just comment this line out, then the default exit code will be 0. Okay. So that is what the exit code is here. And you can see that the child process was terminated by a signal. Okay. Why it is saying that? Because this particular macro would have returned false, and therefore it would have gone to this else part. This particular macro would have returned true. Because I killed the child process, this macro would have returned 2, and this particular macro reads which particular signal number killed the child process. And the kill command sends a signal number 15, which I'll come to that again in the signal chapter. But just for your understanding, kill command also sends some signal to the process to say that you kill yourself. Okay, and that signal number is number 15, and that's why it is basically displaying this information here. Okay, so this is how the parent process can understand whether the child process was terminated normally, whether there was any problem with the child process, if there was an exit value returned back to the parent process from the child process, what was it? The only caveat with the exit code is that it is supposed to be an integer value. Okay, it cannot be a float value. It has to be an integer value, a numeric value. Okay, so that is what we know about, or that is how we can sort of talk about parent and the child relationship. Okay, so whatever we have covered so far is basically just talking about fork and how the parent and child relationship happens. Sharing of the variables, sharing of the files, and understanding the exit code and status from the child to the parent and so on. Now, we had seen that we can run a different program in the child process or a parent process using exec system calls. So we will look at that in the next lecture. Okay, so let me stop here. If you have any questions, I can take them, or else I'll talk to you guys in the next lecture. Any questions? So I've already answered this question.
Sir.
Yes.
Sir, I had a question in quiz 4.
Okay.
In question 3, they've asked to explain the difference between a set of commands using 3 tables.
In which one? Sorry.
Quiz 4, question 3, the last question.
Okay, quiz 4, question 3. Okay.
So, like, how we have to do that? So, do we have to make such 3 tables and then explain it?
Can you tell me quiz 4 is what? File IO?
Yes.
Okay.
In quiz 3, question 3.
Huh. So, what about this one?
Yeah, so how we have to explain it? So, do we have to run each?
No. So remember, we looked at three tables, right?
Yes.
We looked at process file descriptor table, system wide open table, and the inode table. So what you have to do is that at each of these, open command, write command, open command, write command, loop command, write command, you have to indicate the changes that will happen in each of these 3 tables.
Okay.
That is what it's saying. Explain the difference between the following commands using 3 tables, right? So you have to basically understand how each of these file, operation commands are affecting those tables.
Okay.
Understood?
So do we have to make some document or something like that when we have to write it?
Either you can use Word doc with the tables, or you can just draw it manually and put the scan copy. Either one is fine.
Okay, sir. Yeah.
Any other question? All right. Thanks, everyone.